Hello, everybody. Let's get started today. You should have your study guides out in front of you. We are going to first complete the Lego lab that we started yesterday. I wanted to give you kind of a little refresher, just kind of how this works, because I know some of us were kind of running into some problems, which is to be expected. This is kind of a new thing for us. So I wanted to give you that first, and then you and your partner can go get a set of Legos and complete the lab. We'll stay in the classroom today. We won't go into the actual lab. So let me first begin with a couple reminders of how the order we should do things. So we want to start first by filling in this whole before section, right? Which really is just counting up atoms. On the reactant side, that's the left side, and the product side, that's the right side. Then we want to use the correct Lego bricks, okay? And we know the correct Lego bricks because of the little yellow sheet of paper that tells us which bricks is represented by, the color and the atom and all that, to build molecules represented in the equation, okay? So in the case of this one here, which we've already done, but it's kind of a good review, uh, I only see one sodium atom. So I'm going to get one purple brick. That's sodium, and I'll place that down on my desk. This right here is O2. The 2 there, the subscript tells me that this is an oxygen molecule. It's a molecule with two oxygen atoms that are bonded together. So I'll get two, I think they're red bricks, and I will connect them, and I'll place that next to the sodium. Okay, I'll put the plus sign between them. Then the arrow, that's my, produces or yields or turns into symbol. And then I have another molecule that's Na2O. So again, it's a molecule. So I'm going to build these bricks together. Two purples, one red, again, connected together. So it will look something like, let me get to it, something like this. Okay. Now, here are the rules. Okay. The rules state that I'm not allowed to change subscripts. Okay. Now, you might be asking why? Why not? Why can't you change subscripts? Who cares? We're just trying to balance things, right? We are trying to balance things, right? We want the same number of each type of atom on both sides. But think of it this way. If I were to, for some reason, maybe I thought it was a good idea, if I were to add another oxygen atom and connect it to the other two, what would that make this? Ask yourself that. What would that make that molecule right there? It would make it O3. Now ask yourself, is O3 the same thing as O2? And the answer to that is a resounding no. O3 is not O2. We know that when we combine atoms in different ratios, even if it's the same elements, different ratio means totally different molecule with totally different properties. So we're not allowed to do that. That's why we can't change subscripts. So I'm going to backtrack a little bit here. I can't change O2 into O3. I can't change Na2O into Na2O2 because that seems like the easiest thing to do, right? Would be to just add another red one right here. And now I've got it balanced, right? But again, by doing that, I've made this molecule into Na2O2, and that is not the same as Na2O. It's not the same thing. So the only thing we are allowed to do is we are only allowed to make duplicates of things that already exist. That's all we're allowed to do. So what do we do? Well, the first thing I notice is the purple one. It's just the first one there, and I notice that it's unbalanced. So I'll make another purple, another sodium, and I'll add a sodium atom to the left side. And I can do that because one sodium atom all by itself already exists. So that's two on the left and two on the right. But I still have oxygens that are not balanced. So what I got to do is I have to add another oxygen to the right side. But again, I cannot add just a random oxygen atom. What I can do is duplicate this whole thing. That's the only option I can do. So I have to do it. I will duplicate. I'll make another Na2. Sorry for the drawings. It's the best I got. So now I have two oxygens on the left and two on the right. But I have messed up my sodiums again. Now I have two on the left and four on the right. So what do? Well, why don't I just add two more of these? Again, all I'm doing is duplicating what's already there. And so now when I do my final count, I find there are four sodiums. There are two oxygens, four sodiums, and two oxygens. everybody's balanced, everybody's happy. Okay. And so this is kind of the important part, right? When I'm now that I'm ready to rewrite the equation, this time in a balanced form, all I'm going to do is rewrite this here, but I'm just going to change any of the coefficients that I need to. So in the case of the sodium, there was 1, now there's 4, and so I'll put a 4 right there. In the case of the oxygen, I started with 1 and I never actually duplicated that one, so I'll keep the coefficient 1, which means I don't actually write the 1, I just leave it alone. In the case of Na2O, sodium oxide, I duplicated it once, so now there's 2 of them, and so I'll put a 2 there. And then I can recount again if I wanted to. 4 sodiums, 2 times 2, 4 sodiums again, 2 oxygens, 2 oxygens. Everything's balanced. Everything's good. Okay, well, I'll do one more with you. Again, it's probably one you've already seen, but just to be sure. Let's see. This is what I'm presented with. If I were to build it first, right? Because that's what you're supposed to do. Count the atoms first on the before balancing, build it like it's supposed to look, and then start duplicating. I'd probably do the same thing I did before. I'll probably duplicate an iron over here. Let's see. I need more oxygens on the left, so I can't just add another stray oxygen, so I'll build another thing that looks like that. Now I need more on the right, so I have to duplicate that whole thing. Okay, I see 6 on the right, 4 on the left, so I could duplicate the O2 one more time. And then I could duplicate some of those iron atoms. And now I'm done. 4 and 4, 6 and 6, and I am done. So if I were to write this out, I would do 4Fe, because there's 4 of them, plus the coefficient here would be 3, because I see 1, 2, 3 oxygen molecules, makes Fe2O3, and again, there's 2 of them, so I'll put a 2 right there. So that's the idea. So your job is to carry this through all the way to the end, all the way to the end of the lab. Let me pull up that page for you one more time. Right. Let's see, right all the way to this point right here. Okay. In fact, why don't you go ahead and carry it all the way through? I realize that your part A might look a little bit different than mine. Yours might be a fill in the blank instead of state the law, but either way, carry this all the way to the end of page 4. And then, so the sub will pause the video here. You'll go get your Legos, finish up this lab, and then we'll come back together when you're done. Good luck, and I'll see you in a bit. Okay, let's take a look at the post-lab questions. Yeah, see, I have fill in the blanks now, so I hope this matches what you have. But it says, fill in the blanks. Matter can neither be blank nor blank in chemical reactions. The words we like are matter can neither be created nor destroyed. In chemical reactions, the mass of the products must be equal to the mass of the reactants. Okay. Remember, these are chemical reactions. All we're doing is messing with bonds. We're just breaking bonds, making new ones, rearranging atoms. We are not changing any atom's identity. The nucleus of these atoms remains intact. It does not change. And a nuclear reaction, now then we do actually lose a little bit of mass. Not here. Part B says, what is the purpose of balancing chemical equations? The purpose is so that mass, or matter, whichever you prefer, is conserved. If we didn't balance chemical equations, then we wouldn't be conserving matter. And that's not okay, because we know that chemical reactions don't create or destroy matter. All right, part C says, in a combustion reaction, methane, which is CH4, reacts with O2 to produce water and carbon dioxide. Write a balanced chemical equation for this process. If you want to use Legos, or I guess if you did use Legos, then you can. But I'm hoping by now you can kind of see, and this is where we want to end up, we don't need Legos. We don't need a model to do this. If I write it first in its unbalanced form, I'll simply have CH4 plus O2 as my 2 reactants. I'll have H2O and CO2 as my 2 products. And now I start balancing. the first thing I notice is carbon. It's the first element written, and I can see that carbon is balanced right now in its current form. There's one on each side, so I'll leave that alone for now. I notice the hydrogens are not balanced. I have 4 over here on the left and 2 over here on the right. So what do? Again, don't change the subscripts because that changes the identity of the molecule. But I can change coefficients. What if I put a 2 right here? If I put a 2 right there, 2 times 2 makes 4. So now I have 4 hydrogens on both sides. We're headed in the right direction. On the left side, I have 2 oxygens. On the right side, we have to do some careful counting here, right? I've got 1 oxygen per water, 2 waters total, so that's 2 oxygens, plus 2 more, that's 4 total. So to be clear, 2 oxygens on the reactant side, 4 on the product side. How do I balance it? Well, let's put a 2 right there. 2 times 2 makes 4. So now everything is balanced. I didn't change anybody's subscript. I just changed coefficients. That balances equations. Okay, so let's go over to this page and let's try a few more examples. Okay. Again, the rules are pretty simple. Okay. I put some steps here because I've been balancing equations for a long enough time that I've kind of grown to recognize that it's helpful to do things in a certain order. I hope that makes sense. And I guess I should say you don't have to do it like I do. You don't have to do these steps. Like if you want to just kind of go for it, kind of make it up as you go along, start changing up coefficients, erase things if you have to, and go back and change, you totally can. I've just found that if I go kind of through these steps and do things in this order, things tend to work out in my favor. So let me show you these steps and you'll write these down. Typically what I do, sorry, this should say 5 and this should say 6, or 5 and 6? No, 4 and 5, sorry. This should be a 4, this should be a 5. I generally write the equation from names first. So in these examples here, that step is kind of irrelevant because you're already given the formula itself. So all you have to do is balance. But down here, you'll start to see, oh, I don't have symbols yet. I have to go from word to symbol. So that's really the first step, but we'll get to that. We already have a symbolic equation, so that's good. 2 there is, again, kind of that big reminder. Don't mess with subscripts. Only change coefficients. Step 3, this is where the order starts to become a little bit helpful. I like to start with metals. I don't know. I don't know why. It just kind of works out. So I start with metals. Anything metal, I'll go and change that first. I'll make, and by change, I mean I'll balance the metals first. Then I'll start looking at any other non-metals except hydrogen and oxygen. Okay, so like carbon or nitrogen or sulfur or phosphorus or chlorine or any of those, that's what I'll do next. Then the second to last step, I'll look at hydrogen. And then finally, I'll look at oxygen. And this, you're thinking like, why is this your order? This doesn't make any sense. This feels random. It'll make sense. I promise. You'll see some examples where you're like, oh, I think I see why we did hydrogen and then oxygen, or why we did the metals first. You'll see. So let's try a few examples. This is in your study guide, so do what I do. We've got an equation that says HF, that's hafnium, plus nitrogen, right? Molecular nitrogen, remember nitrogen's diatomic, that's why it's N2, makes hafnium nitride. That's how I would name that thing, right? That's an ionic compound, metal, non-metal, hafnium nitride. Okay, I put a little star down here that says, if you want to, I think it's helpful to make a table. Okay, so you could make your table look something like this. You can say, over here, you can put all your elements. And then you can make a two columns there, one for the reactant side and one for the product side. Okay, and all we're going to do is count. Okay, so on the reactant side, I've got 1 hafnium. On the product side, I have 3. I have 2 nitrogens on the reactant side and 4 on the product side. Okay, clearly everything is unbalanced. I've got some work to do. Okay, I like the table because as I start changing coefficients, I can change the table just to make sure I'm headed in the right direction. So my rules say after step 1 and step 2, I want to balance the metals first, and hafnium in this case is the metal. So I see 1 on the left and 3 on the right. What can I change? I don't want to change any subscripts. I wouldn't want to put a subscript here because that would just unbalance it even more. So I'm thinking I need to put a subscript over here. And the logical answer is 3. So if I do that, this 1 now becomes a 3. And that's why I like the table. I kind of keep track as I go. So hafnium for now is good. Next up would be nitrogen. 4 on this side, 2 on this side. Again, I really wouldn't want to put anything on the right side because that would just further unbalance it. So I'll put a coefficient here, right? What coefficient multiplied by 2 would give me 4? Well, it's a 2. 2 times 2 makes 4. And so that's my answer. I'm done. That's a balanced chemical equation. I have the same number of each atom on both sides of the equation. My work is done. Okay, let's try another one. This is PaI5. Gonna be honest, I don't remember what PA is. If you find it, you can say it. PaI5 makes Pa plus I2, okay? Again, Pa is a metal, I know that. So it can exist as a single atom, but iodine, remember, is another diatomic example. So pure iodine has to be in the form of I2. Let's do the same thing. Let's make a little table. Only have 2 elements to worry about. I like to put the metal first before the non-metals. I've got 1 Pa on both sides, 5 iodines on the left, and 2 on the right. So my steps would tell me get the metals done first, but the metals, as it currently stands, are done. So I can't really do anything there. I have to move on to the non-metals. Now you can probably tell that when I balance the metals, I'm going to when I balance that iodine, I'm going to unbalance the Pa. That's okay. I can go back and fix it. So let's take a look. I've got 5 here on the left and 2 on the right. And if you're thinking, right, these are what we would call these are 2 numbers that don't share any factors, right? So I can see that I'm going to have to change both. Like I'm going to have to write a coefficient here and here to get this to work. So when I see 5 and 2, since they don't share any common factors, there's not a whole number I could multiply 2 by to get to 5. What's the smallest number that both 5 and 2 both go into? That's 10. So on the left side, what times 5 makes 10? That would be 2. I'll put a 2 there. On the right side, what times 2 makes 10? That would be 5. So by doing that, I have changed this 5 into a 10, and I've changed this 2 into a 10. Perfect. But I have also changed this Pa. I've changed that into a 2. So I got to balance that. You can see that looks like an easy fix, right? Let's just put a 2 right there. And now we're good to go. Everybody's balanced. Our work is done. Okay, another one. Now this one, you might be like, ooh, that looks complicated. We've got a lot more elements to worry about, okay? But if you follow the rules, I promise things will kind of work in your favor. So let's make a table first. I like to put metals first, so I see lanthanum and sodium. So 2 different metals to worry about. And then as far as non-metals go, I've got nitrogen, oxygen, and hydrogen. And my rules over here tell me that I'm going to put hydrogen first. No, sorry, that's a lie. I'm going to put nitrogen first, then hydrogen, then oxygen. So that's my whole table. Okay. So initial count, I see 1 of these and 1 of those. Okay, we have a 3 right there, so that means there's 3 nitrogens. Yep. Only 1 hydrogen. Okay, with oxygen, there's actually oxygens in 2 different places on the left side. So we have to count all of them. We've got a 3 here and a 3 here, so we have to multiply those together. That makes 9, plus 1 more, that makes 10. Okay, kind of complicates things a bit. We just have to watch out for it. Not a big deal. Okay, let's do the same thing. I see 1 over here and 1. Yep, 1 over here. Nitrogen, only 1. Hydrogen, I see 3. And oxygen, I see 6. That right? 3 here, 3 here. Yep, that makes 6. So we're ready to start balancing. As it currently stands, both lanthanum and sodium, those are the metals, those are already balanced. Now I can probably see that by going down the list, I'm going to mess that up and I'll go back and fix it. Not a big deal. So nitrogen appears to be the first thing that I can actually fix. So I have 3 on the left, 1 on the right. So I'm going to change this coefficient here. Let's change it into a 3 because that would change this into a 3. But it also changed other things. It changed sodium. Now there are 3 sodiums. It also changed oxygen. Okay. We had 3 oxygens here, and now we have 3 times 3. That's 9. So 9 plus 3 makes 12. Okay. I had to count in 2 different places. Now I've got 12. 3 from here, from this one, and then 3 times 3, that's 9, and then plus those 3 from the other one makes 12. So what do we do? Do we move on to hydrogen and fix hydrogen, or do we go back and fix sodium? My advice, go back and fix sodium first. Okay, that's my advice, and you'll see why. Let's go back and fix sodium. We have 3 on the right, 1 on the left, so let's stick a 3 right there. That changes this into a 3. But it also changes some other things. It changes oxygen for 1. Oxygen had 9 from here, and now I have to add 3. Would you look at that? By going back and fixing sodium, I actually kind of helped myself out and fixed oxygen in the process. And if you look here, how many hydrogens do I now have? I've got 3, which is exactly what I wanted. This is why I do things the way I do them, because it kind of just works out in my benefit for my benefit, in my favor. I can I don't have to spend time erasing and doing all this stuff. It works out for me. If you follow these steps, more often than not, it'll work out for you too. So we are done. We're done. This is it. All right. Let's do it again. Okay. Tell you what, you do this one. All right. I'm going to do it kind of slowly up here, but I want you to do it. Try not to look at the screen until you're ready to actually check your work. We'll see if we get the same thing. Well, go ahead and check if you haven't yet. This is what I've got. 2 zinc atoms plus an oxygen molecule makes 2 zinc oxide molecules. Okay. All right, let's do the same thing. You do it on your own, or if you want to work with a partner, that's fine. And then when you're ready, come back and check your work. Okay, go ahead and take a look. This is what I've got. 2, I think Sp is antimony. I hope I'm right. 2 antimony atoms plus 3 water molecules makes antimony oxide and 3 hydrogen molecules. Oh, good. Yeah. So that's kind of the idea. Okay. We didn't have any examples where this happened, but on occasion, you might find that you have to erase. Maybe you made a coefficient and you want to change it. Totally fine. Totally okay if that happens. So I recommend use a pencil. Don't if you need to borrow a pencil from me, go for it. They're on my desk. Use a pencil. Let's not use pens because we're probably going to make mistakes. Another thing that might happen is, let's say, I'm going to back up just for a second. Let's say instead, let's say I did some work and maybe I went off a little bit and I had to fix some mistakes, but regardless, let's pretend for a minute I ended up with an equation that looked like this. Okay. Take a look at this for a second. Is it balanced or is it unbalanced? If you count up all the atoms, it is balanced. It follows conservation of mass. But you can see that it's not as simple as it could be, right? Each of these coefficients shares a common factor of 2. And so it could be reduced to that form down there. So if you ever find that that happens and you're like, well, I could just simplify each of those coefficients by 2 or by 3 or whatever, you can do it, right? I think the simplest form is probably better. So that could happen, and you're more than welcome to do it. So what I would like you guys to do is on page 6, I would like you to work on these problems right over here. These are simple formula equations that are unbalanced. Your job is to balance them. Make sure that you create tables, you follow the steps. I think it'll work out in your favor. And that'll probably do it for today. You guys can work on this until the bell. Thanks for listening, and I will see you guys on Monday.